series test. The integral test is going to be the last test you will want to use. Okay? You're going to want to exhaust your resources, and then if all else fails, you're going to do the integral test, and you will see why. Okay.
What if the integral test is really easy?
The other one is the P-series test, and that one is 5 seconds. Okay, the integral test is going to be about 5 minutes. Okay. So let's look at this integral test. And let's say that before we do it, let's just talk in generalities, okay? So let's say that I have my first term is 4. Okay. My next term is Grant.
Third term is Bob.
Okay. Okay. My next
Bob.
term is what?
Bob.
Chris. So Chris is. I'm right. Okay. And I have these terms, okay? So I have all these terms that I'm adding up. And I'm adding till I go to infinity. Now, if it converges, let's say that all of that guy converges to a sum of 8. I'm just making this up, okay? So, like, when all of the people add together, it converges to 8. And let's say that I take away the first 2 terms. Is it still going to converge?
Yes.
Yeah. Is it going to converge to 8?
No.
No. Okay, so we're not sure, but we would be 8 minus the first 2. So let's say that I took away the first 100 terms. So I was at 8 and I was at converging. I took away the first 100. Would it still converge?
Yes.
Okay, is it going to converge to 8 though?
No.
No. Again, we don't know. Okay, let's say that I had all of those people again. Back. Like that. Okay, let's say that I had all of those people again, and it diverged. Okay? I took away the first 3 now. What's going to happen to the rest?
Nothing.
So I basically have infinity minus those first 3 terms, which is going to still be, infinity minus a number is infinity. Let's say I took away the first 100 terms.
Same.
Still it's going to be
Infinity.
infinity minus the first 100 terms is still infinity. Okay, so when we go to check these conditions, we want to show that this a sub n is positive, continuous, and decreasing. Now this says for some x, but in reality, it's for some x or n, whichever variable you want to use, for some n greater than or equal to any number. As long as you can show any number, you're okay. The first 100 terms don't matter in the whole convergence divergence scheme. The first 1,000,000 terms don't matter if a series just converges or just diverges. Now to find the sum, it's going to matter. Yes? So as long as I can show these 3 conditions for some number forward, then we are okay to proceed. Okay? So we check the 3 conditions. If those 3 conditions are met, then I'm going to turn this guy into this guy. So then I have this. And do you remember how we have to rewrite that? The limit as, like, b, the bad bound. Yes? And we do some fun stuff. Yes? This is back from chapter 7. This guy could either converge or diverge. If it converges, converges, it's going to equal some number. If it diverges, it's going to equal plus or minus infinity. Yes? So if this converges, then the summation converges. If this diverges, then the summation diverges by the integral test. Now, here's where you make a mistake. Let's say that I got this to equal again 8. Does that mean that this equals 8?
No.
No. Okay? It just means that they are both convergent. That's all. It doesn't tell us what the sum is. Okay? It could be 8. It could be 100. Good? Okay, so that's the integral test. I just see it. Okay, so this one wants me to apply the integral test. So first we need to check our conditions. So the first one I want to show is that a sub n is what? Positive. For some n forward, right? So we have our a sub n is this guy. This is going to be positive when what? N is greater than 0.
Greater than or equal to.
No, it would be 0. Okay.
0's not.
So did we show that for some n equaling a number forward that we are positive? So this condition is good. Let's go to the next one. We want to show that a sub n is continuous. So this guy right here is continuous for what? Is there anything that makes it discontinuous?
No.
Okay, for all n. So for any n forward, right? So this condition has been met.
Upside down.
It's for all.
Okay.
So that symbol right there is for all.
Would all real numbers work?
Yes.
Okay.
Okay, and then the third one we have to show is that a sub n plus 1 is smaller than a sub n. We have to show decreasing. And have we practiced that? Okay, so we can do our setup. So that's our initial. We're going to assume right now that n is greater than 0 so that we can cross multiply and not worry about switching the inequality. Okay? So keep going. You guys can do this. We've practiced this. I'll do it up here, but I don't want you just to copy me. I want to make sure you can do it.
Brains disease.
Let's see if we all get into this. I'll wait. All good to hear. Great, so then what did we do to show this? What did we make? A little graph. Okay, so let's kind of check this. So I'm just going to graph that n squared plus n minus 1. When I plug in 0, I get out negative 1. When I plug in 1, I get out
1.
1. When I plug in negative 1, I get out
Negative 1.
negative 1. When I plug in negative 2, I get out 1. I can see the symmetry happening, right? So there's my sketch of my quadratic. And we are looking for when we are greater than 0. So here we are greater than 0. That was an open circle. So this is true for what? We could say this fractional n, or decimal, or irrational, whatever it is there, but I just want some integer value. So what's the first one I could pick? 1. So true for n greater than or equal to 1. Is this guy true for n greater than or equal to 0?
No.
No, because back here we're negative, right? Okay, so that's the first integer value I can pick. So we have shown that the conditions have been met for some n going forward. Yes? Questions about that part so far? Okay, now the conditions are met, we get to take the test. And what is the minimal n that we are going to pick to go into our integral here? What am I? Yeah, the minimal n that we found was 1. So we're going to use the 1. Okay, so we're going 1 to infinity of n over n squared plus 1 dn. And some people like to use x's to do this work. I just like to keep it all in terms of n. Up to you, completely.
I mean, just keep it to what the variable is.
I like
my opinion.
Okay, so let's replace the infinity with what variable?
C.
C. C goes to infinity. Okay, Thor, my question for you. We gotta think back to chapter 7. Is this an arctan? Why? Yeah, because we have an extra variable of that n. It would be arctan if I just had a number. Agreed? Okay, so Thor, which one is this? It is an ln. What am I missing for the ln? A 2. In order to have u prime over u. Agreed? So what do I have to put out in front?
1/2.
A 1/2. There's my antiderivative. I still need to evaluate from 1 to c. So as the ln goes to infinity, what do I get out? Infinity, remember the graph of ln, right? Keeps going up at a slow rate, but it's going up. Infinity times a half is still infinity, and infinity minus this number is still infinity. So I know this integral diverges. Remember how we practiced writing that? So what can I say now? Therefore, this guy diverges by the integral test. Woo! No, but I did teach in DC for 3 years. Yeah, in the most diverse high school in the nation. So, yes.
DC,
A lot of experience with gangs.
Because you've got a lot of foreign people.
Oh gosh. Okay. So. Alright, so, is this okay? Now, let's just pretend, because we like to pretend, let's pretend that this equaled 2. Okay? So here's my little pretend guy. If that equaled 2, does that mean that this guy equals 2? No. Okay? That's not what this means. Could it equal 2?
Yep.
Okay. It just means that this guy does what? Converges. Okay? I'll prove this. Okay. So she wants to know, how do I find when it converges too? It's really difficult, but you can get a better and a better and a better approximation. I'm going to teach you guys throughout this unit 2 different things. A Riemann sum, or not a Riemann sum, sorry. A alternating series remainder and a Taylor series remainder theorem that will approximate for that. I'm going to show you very quickly, this guy is extra. I'm not teaching it, you don't have to know it, but it allows you, this is the infinite sum right here, to find this interval that the sum could lie in. So it's pretty cool. It's by using a partial sum with an integral and the next term divided by 2. Partial sum and the integral, but minus, see, that's the only difference. And here is a quick little example of how they applied this. And again, this is all extra. If you want to look at it, it's pretty cool. You don't have to know this one. You will have to know the 2 that I teach you. But look how close they got it by this process. Okay, Shannon? Okay. So it's kind of a limiting process to find it. Okay. Are you ready for the really hard one now? There we go. P-series. So if you're set up in something like this, so basically, let's say I have 2 over into the 4th. Let's say I have 2 over into the 1/2. Or let's make it 12. Let's say I just have 1 over n. All of these guys are set up in that form. Do you agree?
Yep.
When I see this setup, this is going to be my p-series. And this is how easy it is. If p is greater than 1, then the series converges. If p is less than or equal to 1, but greater than 0, then the series diverges. And again, it all has to do with that infinite summation. Okay? And this guy is going to help approximate a lot of things when you keep going into advanced math. But for now, we just use it for the test. All right.
But if P is less than 0.
Hold on. Go. It might have been. I have to look. I don't remember off the top of my head. When P is less than 0, it's going to be a different test. Okay. So, a special one, and that people always forget, is this harmonic series. And that is when you just have 1 over n. 1 over n diverges. I'm going to die if I have to listen to my son play the harmonic one more time. Oh! Okay. Just a little math device. Diverges for the harmonic series. Okay?
Can't be that bad.
I think it's pretty adorable, actually, but it's just a mnemonic device. Die if I have to listen to him play the harmonica one more time. Okay, so the harmonic series is 1 over n, and it diverges. And again, and on the side note, you guys can look at on your own. So let's go do these 2, and then we'll do an AP example. And I know I'm going a little bit quick, but we have some people who are leaving in like a minute, so try to get them through the notes. Okay, the harmonic series.
Diverge.
This this one diverges by the p series.
Test.
Because p was equal to 1. Whew, that was a toughie. Tori, what's p here? What's our p value on this one? So we want to look for when it's set up. Oops, too far, yes. So we want to look to where it's set up 1 over n to the p. So the p is that number that it's raised to. 3. And by the conditions, what does that tell me? This converges by the...
Now, does the P series tell us where it converges at?
No. Again, we would have to do some more stuff to get that approximation. Okay, so last example, which is awesome. This is an AP example I thought was really cool. How they can bring in something of a question that I wouldn't have thought to ask in a new way. So now they're saying for what values of P will both this series and this series converge? What is the setup? What type of series is this one? This is the P series. What type of series is this one, Jackson? Think of P as just a number, like let's say it was a 1/2 or a 3/2 to the n. Which one's that? Do you remember what it's called? G. Yes. Okay, so this is set up for geometric. And they just want to know for what values will both of those converge. So it's basically, do you know your conditions? Okay. So on this one, this 2p is actually kind of like the p value. And in order to converge, it has to be what? Greater than 1. So partially I know that p has to be greater than 1/2. So there's that part.
That gets you your answer. Or at least severely narrows it down.
Yes. Okay, so now let's come over here. Geometric series says that this is now my what value? R. And that the absolute value of R has to be between 0 and 1. What can I do to both sides here? Multiply by the 2, because absolute value of 2 is just 2. So now put these two together and find your answer.
Boom. So this is great.
Yeah.
Now you get your sign confused. You could use it.
Ready, what'd you get?
C.
Alright, so the answer is C. Okay. So I know some of you are leaving.